AQA A-level physics, electric field strength. And this chunk of the specification is what we'll be covering. So now, electric fields. An electric field is a region of space where charges experience a force. You might remember that a gravitational field is a region of space where masses experience a force. This is an electric field, a region of space where charges experience a force. Now, the direction of the field is the direction of the force that would act on a positive charge in the field. So this is a kind of difference between electric fields and gravitational fields. Electric fields can be repulsive or they can be attractive. If the charge producing the field is positive, then the arrows on this diagram go outwards. Because if I put a positive charge here, then the force is away. Okay? If the charge producing the field is negative, then if I put a positive charge here, it would be attracted to it. So the arrows go inwards. So both of them are radial, but it's important the direction of the field is the direction of the force that would act on a positive charge in the field. And then electric field strength is defined as the force per unit charge, newtons per coulomb. You remember, I'm going to keep comparing it with gravitational fields. We had the strength of a gravitational field is the force per unit mass, and that was newtons per kilogram. Here we have the force per unit charge, and it's newtons per coulomb. Now, for a radial field, again, this is so similar to what we did when we talked gravitational fields. If we combine this E equals F over Q with Coulomb's law, which is F is, I'm going to just say K Q1 Q2 over R squared, then we get this expression for electric field strength for a radial field. The field strength due to a charge Q at a distance R is given by E is KQ over R squared, 1 over 4 pi epsilon naught Q over R squared. So have a go at this question then. We've got this Van de Graaff dome. It's got a charge of plus 1.7 microcoulombs on it. Calculate the field strength due to this dome at a distance of 50 centimeters from its center. What force would act on a small charge that carries doodah at this distance? Stop the video, do it, pen, paper, calculator, and the answer is 3, 2, 1. There you go. Now, they were non-uniform fields, radial fields. For a uniform electric field, well, the way that you produce a uniform electric field is with two metal plates. And you basically just put a voltage across these two plates, and that will produce a uniform field. Looking at the field lines, I can tell that it's uniform because they are evenly spaced. You remember that when the field lines are closer together, that means that the field is stronger. So if the field lines are evenly spaced, that is a uniform field. That means that the field strength is the same everywhere. Notice as well, we have the positive plate and we have the negative plate, and the field goes from positive to negative, because if I put a positive charge there, then the force on it is going to be in that direction. So that is the direction of the field. What does the electric field strength depend on? Well, it will depend on two things. It'll depend on the voltage across the plates. If I turn up the voltage, then the field will get stronger. And it will depend on the separation, how far apart they are. So if they're separated by a distance d, then if I make d smaller, then the field gets stronger. Okay, now consider this. We've got my two metal plates and we've got an electric field, and we've got a little positive charge, Q plus. How much work would I have to do to move that charge from that plate to that plate? How much work would I have to do? How much energy would be transferred? Now, I would have to do work because I'm working against the field. Yeah, the field would push it back again. So I would have to do work. How much work would I have to do? Well, now, first of all, work equals force times distance, isn't it? But we also have work equals QV, which is one of the very first equations we did in electricity. Energy transferred is Q times potential difference. If I combine them, I get FD equals QV. And if I rearrange it, then we will see that F over Q equals V over D. So both of them are electric field strength. So electric field strength, E equals F over Q. That's our definition of electric field strength. And now we also have E equals V over D, which is very useful. It tells us that electric field strength can be measured in newtons per coulomb, and it can also be measured in volts per meter. So you can use either of those. It depends on the question really, but technically you can use either. A newton per coulomb is equivalent to a volt per meter. One thing that you need to remember, however, for any electric field, E equals F over Q, for any electric field. This equation here, E equals V over D, is only for uniform fields. Only for your two parallel plates, E equals V over D. If it's a non-uniform field, you're not allowed to use it. Here's a question for you to have a go at. It's based on a very famous experiment done by an American bloke called Henry Millikan. He got a value for the charge on an electron. Okay, but nevertheless, you have a go at this. I'll show you the answer in 3, 2, 1. And there you go. Notice that the charge Q there is, that is actually, that's 3 electrons. That's what that is. Okay, now consider this. We've got an electric field. We've got two parallel plates. We've got a positive plate at the top. We've got a negative plate at the bottom. So my electric field is in that direction, isn't it? Yeah, there's my electric field. And we've got an alpha particle, which is whizzing along. Okay, this alpha particle zipping along, as they tend to. It's in a vacuum, so don't worry about banging into air molecules or anything. What is the alpha particle going to do when it enters the field? What effect will it have on the path of the alpha particle? And what energy transfer will take place? Think about it. Well, what the alpha particle is going to do is its path will be parabolic. Okay, it'll go wee like that, depending on the strength of the field, of course, but its path will be parabolic. It will be the same as a projectile. Do you remember projectiles when you did forces? If you drive a car off a cliff, I'm not suggesting you do that, but if you were to drive a car off a cliff, its path would be parabolic as well. Now, why? Because horizontally, its velocity doesn't change. But then in this direction here, it's going to accelerate. The car will accelerate due to the gravitational field. The alpha particle will accelerate due to the electric field. And what we'll get is this two-dimensional motion. So the alpha particle will accelerate in that direction, okay? And in that direction, it'll go at a constant velocity. We end up with a parabola. And you can treat it just like you would a projectile and use your Suvat equations to work out things, velocities and stuff like that, displacements. The energy transfer is electrical potential energy will go to kinetic energy. Obviously with the car, its gravitational potential energy would go to kinetic energy. So this hopefully will be demonstrated to you by your teacher at some point. It's a special tube called a Teltron tube, and what you have is you've got an electron gun which is firing electrons into this. The whole thing's in a vacuum, and so electrons are being fired into this region here. So electrons coming out of the electron gun, and what you can do is you can have an electric field there which will deflect the electrons, and you can also have a magnetic field as well. These big circular things are electromagnets, Helmholtz coils they're called, and you can produce a magnetic field, and by balancing the two fields you can work out the specific charge E/m of an electron. Okay, and then Millikan got a value for E, so then you can work out the mass of an electron. But anyway, what happens to an electron when it enters an electric field? And it will deflect like this. So have a go at this. This is a combination of lots of different things. You should be able to do it now. Bit of SUVAT involved as well. So electrons enter this field after being accelerated by a PD of 150 volts. The plates are 6 centimeters apart. They've got 110 volts across them. After traveling a horizontal distance of 9 centimeters, they are deflected vertically by 2.5 centimeters. Mass of electron is doodah. Work out all of that. So pen, paper, calculator. Don't be lazy. Pause the video, get it done. And the answers are... Okay, so the kinetic energy in joules of the electrons is EV, where V is the accelerating voltage, which is 150 volts. So that's my kinetic energy of the electrons. The horizontal velocity, if I put that energy equal to a half mv squared, I'm ignoring relativistic effects. A very little, a useful equation, yeah? You know, kinetic energy is a half mv squared. So, you know, off the top of your head, remember that V is root 2ke/m. It's one of these little equations which, you know, it's surprising how many times you actually need it. So there's your velocity there. The time they spend in the field. Well, we know the horizontal velocity that way, and that won't change. So we can just do distance over time, because we know the horizontal distance. The electric field strength is V/d. There's your voltage across the plates there, and that's how far a plates apart they are, so we know the electric field strength. The force that acts on the electrons, well, E equals F/Q, so F will be EQ, yeah, or E, big E, field strength times little e. The acceleration, F equals ma, so A equals F/m, and then you can SUVAT, and it'll be kind of vertically, in this case, it'll be S is a half AT squared, won't it? Because S is UT plus a half AT squared, and U is 0, and you get the answer 2.5 centimeters, and I realized actually that actually gave you the answer there, but you get the same number. That's crazy if you've done it right anyway.